our last practice exam problem, so question 4, which is mussels, not muscles. So one of my old colleagues basically worked with studying mussels in the Niels Holton Anderson group at MIT. Really interesting sea creatures. They stick to rocks as they're consistently pounded by waves. And the adhesion is basically mediated by a polymer-like material, or you could model it as such. So this group has done several different, basically 3 different polymer gels, as you can see here, and we've run some dynamic mechanical testing. So before we get started, we know that our G prime, this corresponds to our, right here, actually this corresponds to our loss modulus, so this is the loss, i.e. viscous, out of phase, phase. Again, this dominates at temperatures that are very, very high, at frequencies that are very, very, very low. Also dominates at our strain rates, gamma dot, that are very, very, very low, and at times that are very, 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 very long. Time temperature equivalent. Ng prime is essentially the exact opposite. So temperatures very, very low, frequencies that are very, very, very high, strain rates that are high, and then times that are very short. And they are in phase, they are elastic, all these different differences between, again, and this is not the this is the storage modules. So before we get started, we know we're going to be kind of asked some questions on this. One of the interesting things about this gel is you could see that our G prime for this gold, for example, we could see here that for all the frequencies, angular frequencies here, we need to be careful. So this is omega equals 2 pi f, so we want to figure out what f is. But we'll get back to that in a second. But here we can see for this gold gel that our G prime is always larger than our G double prime. So this polymer, for all frequencies measured here, will always behave like an elastic solid. If we look at our this black, gel as well, you can kind of see the same kind of behavior. So we're always going to behave like an elastic solid for this material here. It's only this red gel where we can see that G prime is dominated, as we might expect, at very, very low frequencies, low strain rates, long times. And it's only until we hit this crossover event, which occurs, I'm going to say, so for this red, my omega equals 1. So we know that our F is equal to 1 over 2 pi hertz, and our relaxation time is equal to 1 over F. So we know that for all these frequencies and all these the black gel and the gold gel are going to behave like an elastic solid. So for all of the, kind of again the inverse, you can look at these frequencies. All of these times, if you take the inverse, they'll behave like an elastic solid. But for times less on this side, we're going to behave viscous, and on this side, we're going to behave like an elastic solid. But frequencies, again, lower, frequencies lower than 1 over 2 pi, we are going to behave like a viscous fluid. So very, very, large times. So you just do that inverse relationship there. But again, for smaller times, as we increase frequency, we're going to behave like an elastic solid. So let's see what the problem is actually asking us to do. Describe when each gel behaves like a viscous fluid, when it behaves like an elastic solid in terms of frequencies. Done that. We also did in terms of times. Relaxation times of each gel. So if you're looking at these values, the relaxation time here is like infinite, or it's not we're behaving like an elastic solid for the gold and for the black gels, and we actually already have the relaxation time for the red right there. So excellent. Turns out there are 2 different species of mussel. One that exists near the shore break, where the waves, frequencies of waves hitting the mussels are extremely high, and deep sea mussels that encounter waves at much lower frequencies. Mussels near the shore break will have feet triangles that deform elastically, while mussels in the deep sea, again, deep sea mussels, waves, much lower frequencies, will behave like in a viscous manner. So the elastic response near the shore break will typically have a very stiff modulus. So which gel will best mimic the mussels near the shore break and at the deep sea? So near the shore break, we need to behave, again, high frequencies, we need to behave elastically. So because basically the frequencies are hitting it very high. So we need to make sure that they deform elastically near the shore break. So really, our only 2 options, or actually, which the best option for shore break, because we need to also make sure that it has a very stiff modulus as well. If we look back at these gels, we know, oops, something's happening here. Oh, it's not liking my figure anymore. Let's back out of this real quick. Oops. Uh-oh. I think it's time for, here we go. Very a little bit better. If you see these gels, the black and the or our yellow, or our gold gel are both good candidates because they're going to behave very elastically. But we can see that the gold gel has a higher storage modulus, a higher stiffness. So that's going to be the gel that we're going to kind of stick with. So the gold would be best for the shore break. The best gel for the deep sea needs to behave viscously. That has to be the red gel. So that must be deep sea because that's the only one that behaves viscously. Must be red. This one here near the shore break has, I'd say, orange for sure. Now, if we had to pick one gel to make a synthetic mussel that can survive in both environments, what would be the gel? Well, again, it would have to be the red gel, right? Because we've already established that that is the only gel that can behave both like an elastic fluid, or excuse me, an elastic solid and a viscous fluid. Fantastic. So now we're looking at, the Nielsen Ladders Group is decided to use nylon. So nylon 610, 4, 6, 10, and 12. You can kind of see the chemical structures right here and the differences between them. We now need to kind of look at this loss tangent as a function of temperature and explain the peaks in this plot, what types of motions can be occurring, and why do they all share the same peak? Well, all of these peaks seem to be kind of occurring at the same point. And I'm not going to say that this is a TG transition for this alpha. Why am I not going to say that there's not a clear distinction here? Because based on this chemical structure, the number of carbons in this backbone is changing. And you can kind of see that here. So 4, 6, 10, and then 10 and 12. So as we change the number of carbons in the backbone, we're changing those numbers of intermolecular interactions. So I'd expect there'd be a slight shift in your glass transition temperature, but I don't see that here. So these peaks must be kind of corresponding to some type of rotation around the backbone. So this alpha, beta, and gamma. So if we look at the kind of the structure here, maybe again it's some cooperative wiggling of monomer units, although there should be a little bit of shift there. So really, we're only looking, let's actually take a look at this here. So C, H, and H. We're probably looking at kind of, or actually, CH, CH, yeah, that's okay. We're probably looking at some type of motion around this backbone here, because that's the only thing that can explain like the type of motion that's not going to kind of change as a function of, the only thing that's changing in this nylon structure is the number of carbons in that in your monomer unit, in your repeat unit. So if we see that these same peaks occur for all these different polymers, they must be occurring. There must be kind of some rotation that's kind of continue, or that's not changing as a function of the backbone. So it'd be a little bit different. And that's why I'm saying that this alpha cannot be that TG. You could propose again a lot of different mechanisms, but you want to say, okay, the easiest mechanism is probably this rotation of the hydrogen around a single carbon bond. So that would be here. Maybe here you're looking at a rotation of H around your N for your beta. It's a little bit more difficult, especially. And then maybe here at higher temperatures, maybe you're breaking, because at some point in here we have this C double bond to O and N to H. Maybe here you're breaking kind of this hydrogen bonding that could possibly be occurring between these molecules here or between different chains. So that could definitely be occurring, and maybe that's like magic temperature where those hydrogen bonds can break. But again, I wouldn't classify this as a TG. Why? Because TG we know is going to change depending on those number of carbons in the backbone. Excellent. And finally, we have this family of our PMMA, our methyl methacrylates. So you can see this side group is basically growing between them right here. So here, 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 not too thick, and then small, small. So draw a potential plot of the loss tangent versus temperature for these polymers. Will the peaks remain the same for all the polymers? Why or why not? So I'm going to go ahead and just do a couple of examples. I'm going to call this my red, blue, my green, and then let's go ahead and call this, let's get purple in here. So if I'm doing my graph of temperature versus the log of tan delta, I know that this polymer with the largest, these are all amorphous polymers, so there's not going to be kind of that TG. So I might have some shift here, something here, and then something like this. I know that for the rest of these polymers, so let's say for blue, for example, I know that blue with the smallest side chain, or actually red, excuse me, red with the smallest side chain, that is going to have a peak right here. Now there could be some peaks that are conserved. So what peaks could be conserved? Again, maybe it's the rotation of this double bond over here, or this this kind of not methyl group, but this rotation around this double bond here, or maybe this methyl group here around this bond. So there could be some peaks that are conserved, but the peaks that are going to shift are going to be the ones that are again associated. Let's say that there's a peak right here too. It's going to shift the other direction. Actually, let me go ahead and undo that. So let's say I have a peak like this, and a peak like this too. So why are these peaks shifting to the left? Well, or in what type of motion can they be corresponding? So what's the difference between here and here? Well, the purple has a higher thermal energy. So that could be related to the rotation again around this big bulky side group, this guy rotating in your PMMA structure. So let's draw it out, or HEMA. CH3. I'm going to just do double bond C, oh, yeah, double C, H, H, and then let's just go, and you have this big, bulky side chain here. So these shifts, let's call this, we know this is alpha, beta, and then gamma. The beta and gamma peaks could be correlating to, again, some type of motion of this side group around here. So it could be wiggling, it could be full rotation around here. So the full rotation of this huge bulky side group would be beta. Wiggling would be gamma. Why? Because, again, they occur at these, gamma occurs at a lower temperature, thermal energy, than these beta peaks. But those peaks will shift because there's a difference, again, in that chemical structure here. So we have to kind of, again, correlate, and we could see that if there's some motion associated with the side chain here, there's going to be a shift here. The reason, or one of the ways we know that what types of motion these are corresponding to, they have to be motions around kind of this backbone and not kind of these cooperative motions of repeat unit movements. Why? Because we can see that those cooperative motions will be difficult here because we're increasing the number of those backbone units. But if we're just looking, if the peaks are the same between all these and the only change in structure is the number of backbones, then it has to be related. These molecular motions must be rotations around that backbone, something that does not change. Whereas here, if we're thinking about peaks that may change, is if you have like these big, if we're changing the structure and the length of the side group between all these molecules, you're going to get some types of motion that'll change because, again, it's going to be harder to rotate those around. Excellent. So again, there's lots of different answers for those types of questions, but you want to, again, justify it in terms of what's changing in the structure, how much thermal energy is required to move, and then after that, you're good to go. So that is it. We are officially through both practice exams for this class, and you are finished with MEC 202. So study hard. Let me know if you have any questions, and good luck on the exam. And thanks for participating in this class. All right, I'll see you all next time. Thanks. Bye.